Okay, in this video we are going to introduce the determinant. The determinant is going to be another operation on matrices that takes an n by n matrix, a square matrix, as an input and gives you a number as an output. So this is what the determinant is going to be. But the way that we compute that number is much different. It's much more complicated than the trace where we simply sum down the diagonal. Okay, so the determinant is going to involve all the entries in the matrix, and we're going to see that the determinant is going to give us information about that matrix. It's going to give us information on things like whether or not that matrix is invertible. Now, the trouble with defining the determinant is that it's difficult to give a formula, an explicit formula. That's not to say that you can't give an explicit formula. Maybe I'll even put it down at the bottom of the page here. There is an explicit formula that you can give, but it's a complicated looking formula. So the way that we're going to define the determinant is we're going to give a recursive definition. So we're going to define a 2 by 2 determinant, and we've actually seen 2 by 2 determinants. We saw them when we did the cross product. Then we'll see how to define a 3 by 3 determinant in terms of 2 by 2. Right? And then a 4 by 4 determinant, well, you'll take a 4 by 4 determinant, you'll break it down into 3 by 3 determinants, and then each of those 3 by 3 determinants becomes a 2 by 2 determinant, and so on. Okay, so determinants show up quite far back in the history of mathematics, and one of the original uses was, it's determining, here's the determine in determinant, is determining whether or not a system of n equations in n variables has a unique solution, right? So we and so you can guess, here's where you can see the connection with invertibility, right? We know that for n equations in n variables, uniqueness of the solution is kind of the same thing as invertibility of the coefficient matrix. What's interesting is that actually we're going to define a determinant as something that you do to a matrix, but determinants actually came along much earlier than matrices, right? We've got more than 2 millennia here. Right, you can find examples of determinants going back to I think the earliest written examples we have actually go back to China. You might have guessed ancient Greece, but actually I think China gets the credit in this case. So there are a number of applications of determinants. Solving systems of equations is one. You'll see determinants if you ever take a course in multivariable calculus. Determinants show up in area and volume computations. They show up in change of variables for multiple integrals. You find them in differential equations. There's something called a Wronskian that shows up, which is also computed in terms of determinants, but determinants with entries that are functions. So there are lots of places where determinants show up, and they really do go quite far back. One of the so I mentioned there is a formula, and just to kind of convince you that we don't want the formula. Okay, so if I give you a matrix Aij, n by n matrix, one way to define the determinant of A is it's a sum over all permutations. So sigma here is a permutation of the entries. It'll look like this: A1 sigma of 1, A2 sigma of 2, down to an sigma of n. So a permutation is just some sort of reordering of the numbers 1 through n. So any way of kind of changing that order. Except there's a sign factor that comes in here. There's a sort of -1 to the, well, let me write it this way. -1 to the, I'll put these absolute values around. And this is either sort of 0 or 1, and this thing is called the sign of the permutation. And the way you calculate the sign of a permutation is you figure out when you do that reordering, you count how many times did you have to flip the numbers to get to your reordering, and you see whether or not that number is even or odd. And again, if you've never seen a permutation, this may not mean anything to you, and we don't want to use this formula, okay? Because we're not going to spend time learning about permutations, and even if we knew about permutations, this is still a really messy formula to use. So there is a formula. It's not one that you want to try to use. We want to use this recursive definition. Okay, so 2 by 2 determinants we've done before. We saw them in the cross product, right? If I want to calculate the determinant of a 2 by 2 matrix, remember what we do. We multiply the diagonals. We do A times D, and then we do B times C, right? And the main diagonal going from top left to bottom right comes with a plus sign. The opposite diagonal comes with a minus sign. So we do A times D minus B times C. Okay. So that's the 2 by 2 determinant. You'll find either of these two notations, right? DET for determinant, or you'll sometimes see the vertical bars in place of the square brackets that we usually use for a matrix. So 2 by 2 determinants, we've seen those before. We know how to do them, right? We got lots of practice when we calculated cross products. Okay, let's do a few more just in case. If I wanted to do the determinant, let's say 3, 4, minus 1, 6. Remember, the only thing we got to be careful about here are the signs. 3 times 6 times subtract 4 times minus 1 is 18 plus 4 is 22, right? Minus 2, 1, 7, 4 is minus 2 times 4, subtract 1 times 7, minus 8 minus 7, minus 15, and so on. I think we probably get the idea there. Okay, so once you have 2 by 2 down, you can move on to 3 by 3. We'll do 3 by 3 in the next video. One comment before we go on. We can also use 2 by 2 determinants to compute area. I think this was mentioned back in chapter 3, but just in case you've forgotten. If I have a parallelogram with vertices as shown, so one vertex has the coordinates AB, the other vertex has coordinates CD, then the area of the parallelogram is given by this 2 by 2 determinant, where you take the coordinates, you put one set of coordinates as the first row, the other set as the second row, and you compute the determinant. Right? We kind of did this before, but we thought of these guys as vectors, right? And we kind of worked out the area that way. So this is one place where it comes up, and one way that you would kind of see this sort of thing is you could think of this guy as if you started with kind of just the humble square, unit square. Okay, so with I and j, 1, 0, 0, 1, and we know that the area here equals 1. You can think of this, you can think of applying a transformation, the transformation t of x equals ax, where a is going to be, well, I guess I should do it this way, a, b, c, d. I need the transpose of the one that's up there. But notice that taking the transpose doesn't affect the determinant. This is actually true in general. Okay, yeah. So I can think of this parallelogram as the image of this square if I apply this function, right? And so I might be interested in, well, how do areas transform when I apply this function? And so one way I can do that is I calculate this determinant, and that determinant tells me the extent to which this function is distorting areas. And that's where you would, if you were seeing these things in a calculus context, that's exactly how you would see them. Now, if you really want to see why this result is true, why does it give you the area? Well, the area is going to be the area of the big square. So the big square, well, it's not a square, it's a rectangle. So width times height. There's the big area. And then I subtract off, what else do I have to subtract off? I've got to subtract off these two squares. There's one here. There's one there. Notice that both of those squares have area, or again, they're rectangles. Both of those rectangles have area b times c. There's two of them. And then there are some triangles. So this triangle here, and so that one has height b and base a. This one also has height b and base a. There are two of those I've got to subtract, so 2 times 1/2 ab. And I also have to subtract off these guys. Okay, and those ones have, you know, base d, height c, so there's two of those, 1/2 dc. And if you work everything out, AB plus AD plus BC plus CD minus 2BC minus AB minus CD. CD cancels CD, AB cancels AB. BC minus 2BC gives me minus BC, and I do get AD minus BC. So there's the connection to area, and we'll go on from here, and we'll in the next video we'll calculate 3x3 determinants, and actually we'll see that 3x3 determinants are related to volume.